Hello, let's look at using the double angle identities. So I'm starting with an angle theta in quadrant 1, and I know the value of its sine and cosine. If theta is in quadrant 1, then I know its measure is between 0 and 90 degrees. I'm interested in finding the exact value of the sine of 2 theta, the cosine of 2 theta, and the tangent of 2 theta. So let's think about what quadrant or quadrants 2 theta could be in. So if I multiply through that inequality, I have 2 theta could be between 0 and 180 degrees. So I don't know the angle theta, and I don't know 2 theta, but I know it's going to be in quadrant 1 or quadrant 2. And I can determine that once I find the value of the sine and the cosine of 2 theta. So I have what I need, the sine and the cosine of the angle. I can now use the identities to find those exact values. So to find the sine of 2 theta, I take 2 times the sine of theta times the cosine of theta. So I'm using the single angle theta to find the value of the sine of twice that angle. So I take sine of theta is 4/5, cosine theta is 3/5, and I just need to multiply. So 4 times 3 is 12, times 2 is 24 25ths. So we're saying that the sine of twice angle theta, whatever it is, whatever the angle theta is 24 25ths. Okay, so for cosine theta, we have 3 identities. No matter which one you choose, you should get the correct answer, or the same answer. So let's use the first one that looks very much like a Pythagorean identity, but it is not because of the subtraction. So it says take the cosine of the angle theta, which is 3/5, and square it. Take the sine of the angle theta, which is 4/5, and square it, and then subtract. So 3/5 squared and 4/5 squared. And then when I subtract, I get -7 25ths. So the cosine of that angle theta is -7 25ths. Now, of course, you do not have to do this 3 times, but I want to show you that no matter what identity you use, this will give the same value. So let's look at the other 2 identities for double angle identities for cosine. That one is in terms of only using cosine, and one is in terms of using only the sine of the angle, which is nice because if you only have one of those values, you can still find the cosine of twice the angle. So here it says, order of operations, take the cosine of the angle and square it, then multiply by 2, and then subtract 1. So 3/5 squared is 9 25ths. And when I double that, I get 18 25ths. And when I subtract 1 from that, I get -7 25ths. Whoops, 52, close. All right, there we go. Okay, so let's try the other double angle identity for cosine that involves only the sine of the angle. So I take 1 minus 2 times the sine of the angle squared. So the sine is 4/5. I have to square first. 16 25ths, double that. And then subtract. So 25 minus 32 is -7 25ths. So if you have to find the cosine of twice the angle, you can use any of those 3 identities depending upon what you have. So what I notice is that the sine of twice the angle is positive and the cosine is negative. So we're not in quadrant 1 because cosine and sine are both positive in quadrant 1. So that tells me then that 2 theta is in quadrant 2, because cosine is positive and cosine is negative in quadrant 2. And then once we have the sine and the cosine of the angle, we can find the tangent of the angle, which is our double angle, 2 theta. No need to use the tangent identity, use the sine and cosine value and the quotient identity for tangent. So the tangent of 2 theta is just the ratio of the sine of 2 theta over the cosine of 2 theta. And we know how to simplify that complex fraction, multiply top and bottom by 25, and we end up with 24 over negative 7, or negative 24 sevenths, which should make sense that tangent is negative in quadrant 2. There you have it. Fun stuff.